In this section, we're going to learn about polynomial and rational inequalities. The good news is we've already learned to graph polynomials and rational functions, and so this should just be a slight stretch and not a completely new topic. Some steps in solving polynomial or rational inequalities is as follows. 1. If necessary, rewrite the inequality so that all non-zero terms appear on one side of the inequality sign. If the non-zero side of the inequality involves quotients, bring them to a common denominator. 2. Factor the non-zero side of the inequality. 3. Determine the values for which each factor is 0. These numbers will divide the real number line into intervals. You'll list the intervals determined by these numbers. Use test values for each interval and make a table or diagram for the sign of each factor on each interval. In the last row of the table, determine the sign of the product or quotient of these factors. Lastly, determine the solution of the inequality for the last row of the sign table. Be sure to check whether the inequality is satisfied by some or all of the endpoints of the interval. This may happen if the inequality involves a less than or equal to or a greater than or equal to symbol. So there is the method I just listed, and then there's a faster method. And so what I'm going to do is I'm going to show you how to do this method on the first one, and then from there on out I'm going to use the faster method. So in exercise 1a, we have x squared plus 6x is greater than or equal to -8. Now we're going to set this equal to 0, set this inequality to 0. So we'll have x squared plus 6x minus 8, or minus a -8, which will be a plus 8, is greater than or equal to 0. And now we'll see if we can factor this. 8 can be found with a product of 2 and 4, so I'll give that a try. 2 and 4 add to 6, so my binomials are x plus 2 and x plus 4. Now, I happen to know that if I were to graph the function x squared plus 6x plus 8, I would have a parabola with intersections at -2 and at -4. So I can sketch the graph of what that parabola would look like. And one of my intersections would be at -2, and the other one would be at -4. We want to know where this is greater than or equal to 0. So once again, I'm doing this off to the side just so I can anticipate what my answers will be. But using the steps given, we know that with those factors, we have an intersection or a value for the intervals at -4 and again at -2. Since those are my interval chunks or values for where they break, I will write a interval notation format for each interval given. On the left, very far left, we have -infinity, and the right we have +infinity. Writing the intervals, I'll have the interval from -infinity to -4. And since it's greater than or equal to, we'll put a bracket. But for now, let me just list them as parentheses and not include the actual value. -4 to -2 is my next interval. And then from -2 to infinity is my last interval. I need to pick a test value for the far left interval, so I'm going to pick -5 as my test value. I'm going to substitute this into the factors. So negative 5 plus 2 times negative 5 plus 4 gives me a negative 3 and a negative 1. A negative times a negative is a positive, and so this interval from negative infinity to negative 4 is positive. Or we could say it's greater than 0. Now look at this over here. We notice that this is okay to be equal to 0 as well. So I'm going to say greater than or equal to. And that interval will be from negative infinity to negative 4, and we include the endpoint because of that equal to, because the endpoint would actually be 0 as an output. Now let's test a value between negative 4 and negative 2. Negative 3 would be a good choice, and we'll see what we get. Negative 3 plus 2 times negative 3 plus 4 gives me a negative times a positive, which gives me a negative output, and a negative output is not greater than or equal to 0. So we'll put a slash through it. That is actually below the x-axis, and if you look at the little sketch I drew over here on the left, you can see that that is actually the case. And then lastly, let's pick a value that is positive, say 5, as my test value. Substituting that in, I'll have 5 plus 2 times 5 plus 4. Both of those values are positive, so a positive times a positive is a positive. And so my test value produces a greater than or equal to 0 interval. And so my last interval for which this is true is from negative 2, including negative 2, to infinity. So the solutions that make this true are the solutions from negative infinity up to and including negative 4, and negative 2, including negative 2, to positive infinity. This is the interval for which the inequality is true. So my solution is negative infinity to negative 4, close bracket. And I used an open parenthesis because infinities don't have brackets on them. Union, bracket, negative 2, comma, infinity, close parenthesis. As you can see, this can take a very long time. And so one of the best things that I have found is to identify the general shape of the polynomial, factor it, and figure out its end behavior. This way we can assign positive and negative values on each interval without having to do all the test values. So let's go ahead and do it that way, which is a lot faster. And then you will find that it also works for rational functions because the rules for multiplication and sign numbers are the same as the rules for division with sign numbers. In this next example, we have 3x squared minus 3x is less than 2x squared plus 4. I'm going to subtract 2x squared from both sides and subtract 4 from both sides to get x squared minus 3x minus 4 is less than 0. If I try and factor this, I should have two binomial factors that are less than 0. X and x will be the two variables in the binomials, and negative, let's go with 1 and 4. We need to figure out which one will be negative. I believe the negative 4 needs to be the larger value, and 1 will be positive. So my binomial is x plus 1 times the binomial x minus 4 less than 0. If I sketch this, I can see that my roots or zeros of the polynomial would be at negative 1 and at 4. So I'm just going to put dots there at negative 1 and at 4. And then if I were to think of this as a function, it would be an opening upwards parabola with y-intercept at -4, or 0, -4, if you want to think about it that way. And we can now just look at this and figure out where it's above and below the x-axis. The function is positive on the interval from -infinity to -1, and from 4 to infinity. You can see that the function is above the x-axis on those two intervals. It is below the x-axis on the interval from -1 to 4. And so what we want to know is where the function is less than 0. So I can see that it's below the x-axis on the interval from -1 to 4. So I'm just going to label my little sign chart over here, -1 to 4. I'm going to just draw a little dotted line on here that shows me where the function would be above and below the x-axis, and then I'll list my intervals. -infinity to -1, -1 to 4, and 4 to infinity. Notice I did not include the points -1 and 4 because in this case you can see that we don't have or equal to, it's just a less than. So I'm going to pick the interval where it's less than 0, where the function or the curve is below the x-axis. And so my interval for which this is true is the interval not including the endpoint, or open parenthesis, -1 to +4, close parenthesis.